Okay, this question includes a lot of the thermodynamics topic and also touches on transition metals. There are 6 parts to it, A all the way through to F, so I'm going to recommend that you pause on each section, have a go at the question to the best of your ability, and then carry on through the rest of the video to review your answer. So, part A, part B, part C, part D, and finally parts E and F. Okay, so if we start going through the question, we're doing an entropy calculation to begin, so delta S. And the equation that you need to remember very, very clearly to be able to do these is that delta S is the sum of the entropy of the products, take away the sum of the entropy of the reactants. So I can start to put those in, and you can see here that my products, my NO and my H2O, I've got my values from the table, I've colour-coded them, and they are multiplied by the number of moles in the equation. And then I'm going to subtract from that the entropy of the reactants, working in exactly the same way. Once I've put all of that together, I get an entropy change of 181 joules per Kelvin per mole. On to part B, and this is a Gibbs free energy calculation, so you've got to remember what the expression for Gibbs free energy is. And when I start to put those figures in, you can see I've got the negative 905 from earlier in the question. The delta H was provided. My temperature was given in degrees Celsius, so I've needed to add 273 to convert it to Kelvin. And I'm then multiplying that by delta S. But I've made a fundamental error so far. Because entropy is in joules per Kelvin per mole and delta G is in kilojoules per mole, I need to convert my entropy. So I do that to kilojoules per Kelvin per mole by dividing by 1,000. And once I've done that, I get my value, negative 1063. Okay, moving on to part C. So the reaction between ammonia and oxygen was carried out at a higher temperature. How would this change affect the value of delta G for the reaction? Well, let's start again by writing out the expression. Delta G is delta H, take T delta S. In this situation, we know that delta H is negative, and we are taking away T delta S. Now T is always positive because T is in Kelvin, and the lowest temperature on the Kelvin scale is 0. So if delta S is positive, as delta S gets bigger, T delta S gets bigger. And that means that delta G will become smaller, or it will become more negative. Moving on to part D. And we're moving into catalysis here, so part of the transition metal topic. Quite a lot of space here, and there's not a huge amount that you need to write down. So platinum is a heterogeneous catalyst in the reaction between ammonia and oxygen. It provides an alternative reaction route with a lower activation energy. But here we need to describe the stages of that route. And as questions go, it's a relatively straightforward 3-marker. First of all, the reactants are adsorbed onto the catalyst surface. Be really, really careful with that word adsorbed. Don't use absorbed. You absorb in, but you adsorb on to the surface. Now, once they are on the surface, the reactions can take place on that catalyst surface. And once the reaction has taken place, the products are desorbed from the surface. And there you've got your 3 marks. And then finally, we go to E and F. A little bit of redox here. We have got what is the change in oxidation state when NH3 is oxidized to NO? Well, NH3, the H is +3 because there are 3 +1s. Hydrogen is always +1 apart from in a metal hydride. So here it's worth asking yourself how confident you are with those rules for determining oxidation states. Now if the hydrogen makes up +3, the nitrogen must be -3. If I then go to NO, in the NO my oxygen is -2 because oxygen is always -2 except in a peroxide when it's -1. So if it's -2, the nitrogen must be +2. So the overall change here is from -3 to +2. You'd also get the mark if you identified the difference. So you could say the change is +5. And it's oxidation because we have increased the oxidation state. That's an easy way of seeing that it's oxidation. Finally, for the equation, well, we're told that NH3 is reacting with O2. We're told that we're making N2O, but you are going to need to you're going to need to remember that if I combust hydrogen within a compound, I'm going to make water. All that's left to do then is to balance. Now at the moment, I've got one N on the left and 2 on the right, so I need 2 NH3. That means I've got 6 H's on the left, so I need 3 H2O's. And finally, I have got 4 oxygens on the right in total, 3 in the water, 1 in the nitrous oxide, so I need 2 O2 to counterbalance that.